Hi and welcome. So in this chapter, we take a deeper look on the role of capital accumulation in growth. We also look at the effect of the savings rate on the level and growth rate of output. So how do we feature in savings to our narrative? Just a brief history. So since 1970, the US savings rate, which is the ratio of savings to GDP, has averaged only 17% compared to 22% in Germany and 30% in Japan. Okay, so before we continue, can this explain why the US growth rate has been lower than the other countries in the chart we looked at in chapter 10? Also, would increasing the US savings rate lead to sustained higher US growth rates in the future? I think if we look back, we can agree that we've already given the basic answer to these questions at the end of chapter 10. But as a recap, the appropriate answer will be no. An economy's growth rate does not depend on its savings rate. It does not appear that lower US growth rate in the last 50 years comes primarily from low savings rate. Nor should we expect that an increase in the savings rate will lead to a sustained higher US growth rate. This conclusion does not mean, however, that we should not be concerned about the low savings rate in the US. Even if the savings rate does not permanently affect the growth rate, it does affect the level of output and the standard of living thereof. So an increase in savings rate would lead to a higher growth for some time and eventually to a higher standard of living in the United States. So this is what we'll also cover in this chapter. As we have introduced in the previous chapter, the relation between output and capital is at the center of the determination of output in the long run. So the evolution of output and capital over time is represented by this chart. So what does this chart tell us? It tells us that the amount of capital determines the amount of output produced. It also tells us that the amount of output determines the amount of savings and in turn the amount of capital being accumulated over time. So if we start with the first relation, so capital, as we have shown, determines output or income, since output and income are two sides of the same coin. So from income, we can derive savings or investment, because savings determine investment. We can only invest what we've saved, or rather, investment is determined by savings. Hence, they go together. Then the following round is basically our change in capital stock. So what is our change in capital stock? It's basically the capital stock we have now plus the new stock that has been invested. So change means that what is left plus what we've invested, what is new in the new year. Then this again goes around and gives us the initial stage, which is the capital stock. So in a nutshell, capital stock determines income or output, and savings is determined by output. And from what we save and invest, we get the change in capital stock. So let's look at each relation in turn. So the previous figure shows the relationship between capital and savings on one hand and capital investment on the other. So we're basically going to look at the interrelations of these factors with output. So starting with the effect of capital on output, because this is what we left on in the previous chapter. If you remember in the previous chapter, from the aggregate production function, that output is a function of of capital and employment, we derive the relation under the assumption of constant return to scale, that this relation here. So it basically tells us that output per worker is an increasing function of capital per worker. I think we did discuss this in detail in the previous chapter. So it tells us that an increase in capital per worker, which is K over N, leads to an increase in output per worker, but in a decreasing rate. Okay, so we also showed that when capital per worker is already very high, increasing it further have only small effect on output per worker. So we continue from this narrative. So to simplify it, let's drop this one here because it is neutral in any ways. So if we drop the one, we have a simplified notion of the relation. So this relationship is still intact. It still shows us that output per worker is an increasing function of capital per worker, but at a decreasing rate. Okay, so for this chapter, we are going to make a few assumptions, or rather 2 new assumptions. So the assumption 1, we're going to assume that the size of the population, participation rate, and unemployment rate are all constant. So since we know the relationship between population, participation rate, labor, and employment, N, this will also mean that N is constant. The second assumption is that there is no technological progress. So this means that in our function f doesn't change over time. Therefore, this will mean that we take a clear or direct focus on the role of capital accumulation, or rather the relationship between capital accumulation and output. Okay, so the relation between output and capital per worker from the production side is given by this function here. So we have introduced time indices. As you can see, there is T in both output and capital. There is, however, no T in N because we have assumed that N is constant. So the time indexes are introduced for output and capital to show that output and capital change over time while N is constant. In words, this function basically tells us that higher capital per worker leads to higher output per worker. Okay, so this is the first stage. We've established the effects of capital on output. So the second stage is to establish the effect of output now on capital accumulation. So to derive this second relation between output and capital accumulation, we will proceed in 2 steps. So 1, we will derive the relationship between output and investment, and 2, we will derive the relationship between investment and capital accumulation. Let's look at these factors. So starting with the relation between output and investment, you may remember in chapter 3 of your Economics 2 module, we learned that investment I is equals to private savings plus public savings, which is a function of tax minus government spending. Or rather, we said investment is equals to savings, and savings is a function of private plus public investment. So we further make 2 assumptions. We assume that our economy is closed, 1, and 2, we also assume that public savings is equals to 0, meaning that T minus G is equals to 0. In so doing, we then mean that we're looking at the relationship between investment and savings, as savings being private savings, meaning that every savings is private. Therefore, investment is equals to S, which is private savings. We further assume that private savings is proportional to income, meaning that S is equals to small letter s times income. So the parameter S, the small letter s here, which represents savings rate, it has a value between 0 and 1. So this assumption captures two basic facts about savings. One, the savings rate does not appear to systematically increase or decrease as countries become richer. Two, richer countries do not appear to have systematically higher or lower savings rate than poor ones. So combining these two relations and introducing time index gives us a simple relation between investment and output. So that is investment now in certain time or period is equals to savings times output in that time period. So this relation tells us that investment is proportional to output. So the higher the output Y, the higher it is, the higher is savings rate S, and so the higher is investment. Make sure not to confuse between savings rate and savings. So the second step relates to investment, which is a flow. For instance, a new machine produced and new plant built during a given period, and capital, which is a stock. For instance, the existing machines and plants in the economy at a point in time. So think of time measured in years. So a year is represented by T, for instance. And T plus 1 represents the year after year T. And so on. So now, think of the capital stock as being measured at the beginning of the year. So KT refers to capital stock in the beginning of year T, and KT plus 1 refers to the capital stock in the beginning of year T plus 1, and so on. So assume that capital depreciates at a rate of the Greek small letter delta, which is represented by delta. So this means that from one year to the next, a proportion of capital stocks breaks down and becomes useless. So equivalently, a proportion of capital stock remains intact from one year to the next, and that will be represented by 1 minus what is depreciated. So it's the full of the capital minus what is depreciated. So it's 1 minus delta. So given this, it means that the evolution of capital stock is given by this function here, which tells us that capital stock in the beginning of year T plus 1, which is represented by KT plus 1, is equals to capital stock at the beginning of year T adjusted for depreciation, or which is capital stock in the beginning of is capital stock in year T that is still intact in year T plus 1, which is represented by the 1 minus depreciation into capital, and plus the new capital stock put in place during year T, which is represented by investment. So given this, we can now combine the relation between output and investment, and the relation between investment and capital accumulation to obtain the second relation we need in order to think about growth. That is the relation between, or rather from output to capital accumulation. And we'll do that in the next video. Thank you.